the first, I guess you could say, modern conception of an acid and base comes from this gentleman right over here, Svante Arrhenius. And he was actually the third recipient of the Nobel Prize in Chemistry in 1903. And his definition of acids, under his definition of acids and bases, an acid is something that increases the concentration, increases the concentration of hydrogen protons, or we could say protons, when put in an aqueous solution, when in aqueous solution, and that's just a water solution. And then you could imagine what a base would be. You could think, well, maybe a base is something that decreases the protons, and that's one way to think about it. Or you could say it decreases, actually let me write this, it increases the hydroxide concentration. It increases the hydroxide concentration when put in aqueous solution. When in aqueous solution. So let's make that concrete. Let's look at some examples. So a strong Arrhenius acid, and actually this would be a strong acid by other definitions as well, would be hydrochloric acid. Hydrochloric acid, you put it in an aqueous solution. So that's the hydrogen. You have the chlorine. You put it in an aqueous solution. It will readily dissociate. This reaction occurs, it strongly favors moving from the left to right. You're going to have the chlorine strip off the two electrons in the covalent bond with the hydrogen, leaving the hydrogen with no electrons. So the hydrogen is just going to be left as a hydrogen proton, and then the chlorine has just nabbed that electron. It had the electrons it had before, and then it just nabbed an electron from the hydrogen, and so it now has a negative charge, and these are both in aqueous solution still. They're still both dissolved in the water. And so you see very clearly here, you put this in an aqueous solution, you're going to increase the amount of hydrogen ions, the amount of protons in the solution. And we've talked about this before. You'll often see a reaction written like this, but the hydrogen protons, they just don't sit there by themselves in the water. They are going to bond with the water molecules to actually form hydronium. So another way that you will often see this is like this. You have the hydrochloric acid. It's in an aqueous solution, just a fancy way of saying it's dissolved in the water. And then you have the H2O, you have the water molecules, H2O, and you'll sometimes see written, okay, it's in its liquid form, and it's going to yield, instead of just saying that you have a hydrogen ion right over here, you'll say, okay, the hydrogen is actually going to get bonded to a water molecule, and so what you're going to be left with is actually H3O. Now this was a water molecule, and all it got was a hydrogen ion. All that is a proton. It didn't come with any electrons. So now this is going to have a positive charge. And we can now say that this is going to be in an aqueous solution. Hydronium is going to be in an aqueous solution, and you're going to have plus, now you're going to still have the chloride ion, or it's a negative ion, so we call it an anion. Chloride anion, and this is still in an aqueous solution. It is dissolved in water. And remember, all that happened here is that the chlorine here took all of the electrons, leaving hydrogen with none. Then that hydrogen proton gets nabbed by a water molecule and becomes a hydronium. So even by this definition, you might say it increases the concentration of hydrogen protons. You could say it increases the concentration of hydronium right over here. Hydronium ions. So that makes, by the Arrhenius definition, that makes hydrochloric acid a strong acid. That makes it a strong acid. Now, what would be a strong base by the Arrhenius definition of acids and bases? Well, one would be sodium hydroxide. So let me write that down. So if I have sodium hydroxide, sodium Na, that's the sodium, and then I have the hydroxide, that's an oxygen bonded to a hydrogen. So that's sodium hydroxide. And actually, if you wanted to see what this molecule looked like, you have a oxygen having a covalent bond to a hydrogen. Let me do these in different colors. Oxygen has a covalent bond to a hydrogen right over here. And it actually has 3 lone pairs. It actually has 3 lone pairs right over here. It's actually nabbed an electron from somebody, someplace. And so it's going to have a negative charge. It is going to have a negative charge. Actually, I could write it. Well, let me just write it like that. It has a negative charge. And then you have a sodium ion that has lost its electron somehow. So you have a sodium ion that has lost an electron somehow, so it has a positive charge. And for all we know, it could have lost the electron to the oxygen right over here, making the oxygen negative and making the sodium positive. And so this is now positive, this is negative. They're going to be attracted to each other, and they form an ionic bond. So sodium hydroxide, they have an ionic bond because the sodium is actually positive, and the hydroxide part right over here, that is negative, and that's what draws them together. But anyway, you put this in an aqueous solution, you throw some sodium hydroxide into an aqueous solution, it will dissociate into sodium with its positive charge, the sodium ions. And actually, the sodium ion is still part of this. That's what makes it attracted to the hydroxide anion. But it's still going to be in an aqueous solution. And then you're going to have the hydroxide. You're going to have the hydroxide anion. So essentially, this thing just dissociates. This has a negative charge, and it's still going to be dissolved in the water. So aqueous solution. So you throw sodium hydroxide in water, it's going to increase the concentration. It's going to increase the concentration of hydroxide in the water. It's going to increase the hydroxide concentration. And so by the Arrhenius definition of acids and bases, this would be a strong Arrhenius base. This would be a strong base by the Arrhenius definition. Now, and I encourage you to look at that relative to the other definitions, the Bronsted-Lowry definition of acids and bases and the Lewis definition of acids and bases, and see how you would think about categorizing things.